Another neat thing we can do with these ideas of derivatives is try to find the a way to approximate certain values that maybe aren't so pretty to try to find on their own. So say we've got the square root of 25.5. We want to take a guess at what that is. Well, we know the square root of 25 is 5. So we're going to guess something a little bigger than 5. But what do we guess? Do we guess 5.5? Maybe that's a little big. Do we guess 5.0001? Maybe that's a little small. Do we guess 5.25? Do we guess 5.2? 5.03? There are a lot of guesses we could make. And so our goal is to figure out how we can estimate this value using calculus. Maybe we don't need to have an exact answer, or maybe we're trying to figure out how we can find these exact answers. So our approach is going to be to find the equation of a tangent line to our function y equals square root of x at a nicer value, then plug x equals 25.5 into the equation. So here's our idea. We're essentially taking, and if we've got 25 here, here's say 25.5. We've got some sort of equation here. Now we know the square root of 25. That's the thing we had just talked about. And so if we take our tangent line to our graph at this point, and if I can actually line up this pen in the correct manner, not quite, but close. Essentially, we want to see if we can go ahead and look at the equation or the value of the function on the tangent line, because that'll be something that's very, very close. So, well, on one hand, we'll have the value of 25 of the square root of 25.5, but we'll also have on our line the value of the tangent line at x equals 25.5. And these should be relatively close to each other. It might not be perfect, but it should give us a good approximation. So our steps when we do this are first to determine what function we have. So since we're looking at the square root of 25.5, our f of x, or our y, will start off as the square root of x, or just x to the 1/2. From here, we want to pick a nice, or in other words, easy to work with value near our desired x value. So we know that x is going to be 25.5, so our approximation we're going to pick as a. So a will be this quote-unquote nice value. And so since we know the square root of 25, our approximation, or our nice thing, will be 25. Next will be to find the equation of the tangent line for y at x equals a. So if we want to go ahead and find the equation of the tangent line, we need a point, which will be 25 f of 25. Fortunately, this is not too hard to get. That's why we picked it. It's kind of nice. We'll get 25 for x. Well, we knew that. And our f of x value is just the square root of 25, which is 5. We also need a slope, which is going to be f prime of x. So the derivative of this, of course, ends up being 1/2 square root of x. So if we want to find our equation of our tangent line, we just have y equals mx plus b. We know x, we know y. If we're looking at our slope, then we will have our 25 to plug in. So f prime of 5, or sorry, f prime of 25 is going to be 1 over 2 times the square root of 25, or 1 over 10. So in finding our equation, we have 5 equals 1/10 times 25. I don't think I'm running out of ink. We can just use a pencil and that'll work. So 1/10 times 25 plus b. And so this will give us 5 equals 5 over 2 plus b. And so subtracting over, since 5 over 2 is 2.5, we'll get that b is 2.5. So then our equation is y equals 1/10 x plus 2.5. And so we can go ahead and plug in our x, which is 25.5 from before. And we get y equals 1/10 times 25.5 plus 2.5. And so when we do all this, we get that y is equal to 5.05, which will be approximately equal to the square root of 25.5. So this is how we go ahead and find our approximation. So if we look, the square root of 25.5, when we plug in our calculators, is actually 5.0975, yada, yada, yada. But the important thing is 0.049. So we're very close with our estimate of 5.05. So let's talk about, in general, how we would go ahead and think about this idea of a linear approximation. Because so far we've kind of just thrown ourselves in there and say, oh yeah, it's a great thing to do, let's do it. So our idea with a linear approximation is, say we have some sort of function. It's got its ups and its downs and an up and down and up. Maybe it goes over here. What we're looking at is we have some sort of x value that we want to find the f of x value. So this is the f of x that we want to approximate. And what we'll have is we'll have some sort of value that is close to that, a, that is considered easier to work with. Or nice. And what we'll do is we'll find our equation for our tangent line. So this is the tangent to f of x at x equals a. And the value we get on the line is the value we will use to approximate. This should be on the tangent line. F of x. So we've got some function. Our goal is to approximate f of x naught, and so this is the value we want. And so we'll approximate f of x naught by putting x naught into the equation of the tangent line. At x equals a. So our steps will be to find some sort of nice value a close to x naught, and then for our tangent line to y equals f of x at x equals a, we have our point, which is going to be a f of a, and our slope, which is f prime of a. So even knowing nothing else, if we know that we have y equals f prime of a times a plus, technically this y would be f of a, and we don't know what b is, but we'd like to find it. If we solve for b, we'll get that b equals f prime of a times a, this is all negative, plus f of a. And so plugging in then, our equation for our tangent line will be y equals f prime of a times whatever the actual x naught is we had, or x, plus b, which will be minus f prime of a times a plus f of a. Or if we simplified that, y would be equal to f prime of a, factoring out the x naught and the a, of x naught minus a plus f of a, which we will call L of x for the, we're going to call L of x the linearization, because we're using a line, or the linear approximation function. And so again, we could actually, instead of putting our x naught in there, we could just put in x, and then it's a function that can be used to approximate any values near there, and then we can specifically plug our x naught into L of x in order to solve. So let's actually talk about something that's kind of interesting about this formula. Essentially what we're saying is that if we know the y value for our nice thing, and we know the slope, all we're doing is taking x minus a, which is just telling us how far away we are, right? So that's kind of our change and our x value in order to find this linearized form of the value we're looking at. All right, so let's walk through a few more examples of linearization just to make sure we've got the idea. So say we want to approximate this fourth root of 17 using linearization. So first, we need to get a function. And so we're going to say that y equals the fourth root of x, or just x to the 1/4. Next, we want a nice value. And so here we want something that the fourth root of is actually pretty easy for. Well, it turns out that 16 is a good value since f of 16, the fourth root of 16, is just 2. So if you check 2 times 2 times 2 times 2 gives us 16. So then for step 3, we want to go ahead and create our linearization. So L of x will require us to know our point of 16 f of 16 and our slope, which is going to be f prime of 16. And so our slope will be 1/4 times 16 to the negative 3/4, which will give us 1/32. And so in order to create this linearization, we just need to go ahead and use what we know. So linearization will be our slope times our change in x, so 16 minus x, plus the value that we already have, so plus 2. And then last but not least, we're plugging in our 17, that thing that we have. So L of 17 is 1/32 times 17 minus 16 plus 2, or that's 1/32 plus 2, which is going to end up being approximately 2.03125. Actually, that's exactly equal to that. I don't know why I said approximately. And so note that 2 plus 1/32 gives us this value, but this fourth root, which is a little tough to type in, so the fourth root, here is that button. You know what, this is just easier. 17 to the power of 1/4 is 2.030543. So we're actually very close with our approximation. So note that linear approximations often get used in physics. So if we look at the consequences of some equation, sometimes we might need to simplify a function by replacing it with its linear approximation. So one of these more famous examples is when deriving the formula for the period of a pendulum. Oftentimes we'll replace sine of some angle by the angle when looking at the formula for the period of a pendulum. And so the idea then is that you can linearize sine of x with x. So we want to verify this by finding the linearization of the function f of x equals sine of x when x equals 0. So first, we want to make sure we understand what our function is. So in this case, it's pretty clear f of x is going to be sine of x. And here we're also given what a is. A is going to be 0. So near that value, we want to know kind of what our equation of the tangent line looks like. So we need to have our point, which is going to be 0 sine of 0. And so remember the sine of 0 is just 0. And our slope is going to be f prime of 0. So remember that since sine is our function, the derivative of sine is cosine of 0, which is just 1. So that tells us then that if we're trying to create that linearization equation, we are looking at Lx equals 1 times x minus a plus f of a. Or in other words, L of x is just x. So when we are near 0, the sine of x is approximately the same thing as just x. So seems like a lot of steps, but in the end, if all we are doing is finding out some sort of function value for some sort of nice thing, the derivative at that nice value, and using it to try to approximate something else. So say we know that for some function f, f17 equals 6, and f prime of 17 equals negative 2. In order to approximate this f of 17.2, we again know our function is going to be f of x. Our a in this case is just going to be 17. And when we're trying to create L of x, we know our point is 17 comma 6, and our slope is f prime of 17, which is negative 2. So then L of x will be equal to negative 2 times x minus 17 plus 6. And so when we go ahead and plug in 17.2, we'll get negative 2 times 17.2 minus 17 plus 6, which will give us negative 2 times 0.2 plus 6, or simply 5.6. So this will be our idea with this linearization, is we're just trying to get nearby values, use it to create a tangent line, and use that tangent line and rewrite it in a way that allows us to find values that are close by.